Hello, in this video we're going to revisit the idea of finding areas under curves and between curves using some of the new techniques and integrals we have been learning. So the concept behind finding the area bounded by a curve and the x-axis is exactly the same as previously, except firstly you can now integrate new functions other than polynomials, such as trigonometric functions, e to the x, lx and partial fractions. Secondly, you can apply new techniques such as integration by substitution and integration by parts. And thirdly, you're also expected to be able to find the area bounded by two curves, which you can do by subtracting one curve's equation from the other. So in example 1, we're going to be integrating ln x over x. We've been asked to find the area bounded by the curve, the x-axis, and the line x equals e. So we need to integrate ln x over x dx. Well, we can split that into two parts. We can write u equals ln x and v dash equals 1 over x. Okay, there's no point writing v dash equals ln x because that would require us to integrate it. U dash is 1 over x, v is ln x, and then substituting those into the formula for integration by parts, uv is ln x all squared, and then we have to take away the integral of u dash times v, which is ln x over x dx. Now, of course, that takes us back to where we started with ln x over x dx. So if we call the whole thing I, then we've got I equals ln x all squared minus I. So 2I equals the square of ln x, and I is half of ln x squared. So we've integrated it. The next thing we need to do is to substitute the limits in to work out the area. We can see from the graph that it crosses the x-axis at the number 1, and we're supposed to be integrating it between 1, therefore, and e. So substituting e into that, we get half of ln e squared, which is the same as half of 1 squared, i.e. a half. And putting 1 in there, we get half of ln 1 squared, which is half of 0, i.e. 0. So our final area is 1 over 2, a half. For example 2, our function is x cos x. So again, we're going to be using integration by parts. We've been asked to find the area bounded by the curve and the x-axis between x equals 0 and x equals 3 pi over 2. Well, 0 gives us 0 for the function. Pi over 2 gives us 0 because cos of pi over 2 is 0 and cos of 3 pi over 2 is also 0. So we're actually looking at the positive area just after the y-axis as well as the negative area between pi over 2 and 3 pi over 2. So we're going to have to integrate those and then substitute numbers in separately, so that we don't get any cancelling out between the negative bit and the positive bit. So firstly, the integration, x cos x. So let u equal x and v dash equals cos x. U dash is 1, v is sin x. So uv is x sin x. U dash v is sin x. So we've got x sin x minus the integral of sin x dx, which is x sin x plus cos x plus c. So now when we stick our limits in there, we won't need the c anymore. So the integral between 0 and pi over 2 of x cos x dx will be x sin x plus cos x between 0 and pi over 2. Substituting pi over 2 gives us pi over 2 plus 0. Substituting 0 gives us 0 plus 1. So when we finish that off, we get an answer of pi over 2 minus 1. That is the area, the positive area between 0 and pi over 2. Repeating the same process, but with limits of pi over 2 and 3 pi over 2, as you can see, we get minus 2 pi. And that's because that area is below the x-axis. So the actual area is 2 pi. So then when we add the two areas together, we've got an area of 2 pi plus an area of pi over 2 minus 1, giving a total area of 5 pi over 2 minus 1. And then finally, for example 3, we're looking at the area bounded by two curves. The figure shows the curves y equals x squared plus 2x plus 8 and y equals 6x plus 14 minus x squared. Find the area bounded by these curves. So the first thing we need to do is to work out what x values we're going to be integrating between, i.e. where do these curves intersect. So if we put them equal to each other, x squared plus 2x plus 8 equals 6x plus 14 minus x squared. We can move everything to one side so it equals 0, because it is a quadratic equation. 2x squared minus 4x minus 6 is 0. Divide everything by 2 and factorize. Gives us x minus 3 times x plus 1 is 0. So x is negative 1 or 3. And then we can go back to either of the equations and substitute in our values of x. And that gives us y equals 7 or 23 So our two coordinates are -1,7 and 3,23. If we zoom in, we can see that we're correct. So the left-hand intersection point is at -1,7 and the right-hand intersection point is at 3,23. Now we could evaluate the integral of each of these curves between -1 and 3 and then subtract the answers, but they're encouraging us to actually subtract the curves from one another and then integrate that. So we've got 6x plus 14 minus x squared, that's the negative quadratic, so that's the one higher up, and x squared plus 2x plus 8, which is the lower curve between these limits. And we're going to subtract the x squared plus 2x plus 8 from the 6x plus 14 minus x squared. That gives us 4x plus 6 minus 2x squared. When we integrate that, we get 2x squared plus 6x minus 2/3 x cubed. And then when you substitute 3 and -1 into that, we get a final answer of 64/3 for the area bounded by the two curves.